Welcome, my friends! This video will focus on how to build a polynomial if we know the zeros of the polynomial. But first, let's review what a polynomial is. A polynomial is a term, or the sum of two or more algebraic terms whose variables have whole number exponents. For example, 3x squared plus 7x plus 4 is a polynomial with three terms. The terms are 3x squared, 7x, and 4. The expression 10x plus 3 square root x is not a polynomial, as the square root of x is the same as x to the 1/2 power, and only whole number powers are allowed for polynomials. Also, expressions with transformations of variables, such as logs, constants raised to variable powers, and trigonometric functions are not classified as polynomials. Polynomials are typically written in what is called standard form, which means the exponents on the variable decrease from left to right. For example, 3x plus 8x squared plus 4 is not written in standard form. The exponent on 3x is 1, the exponent on 8x squared is 2, and the exponent on 4 is 0. The expression can be reordered as 8x squared plus 3x plus 4, which is in standard form. The degree of a polynomial is the highest exponent on any of its terms. For example, the degree of 3x to the 7th power plus 5x to the 3rd power plus x is 7, as the highest power on any of the terms is 7 on 3x to the 7th. As we will learn as we start to graph polynomials, the term with the highest power will tell us about the end behavior of the polynomial, meaning how the polynomial acts as we get closer to positive or negative infinity. Essentially, the term with the highest power dominates the other terms as we get to extremely high or extremely low values for x, and therefore the function becomes overpowered by the leading term. We will talk more about that later. For this video, we are going to focus on building polynomials given their zeros. Consider the polynomial x squared plus 6x plus 5. Let's say we want to know when this polynomial intersects the x-axis. In other words, we want to know where the zeros of this polynomial are, meaning when y is equal to 0. This polynomial has a degree of 2, which tells us that the maximum number of zeros it can have is 2. This polynomial cannot intersect the x-axis more than 2 times. It could intersect the x-axis less than 2 times, perhaps 1 or 0 times, but the largest number of zeros possible is 2. The way to find the zeros of a polynomial is to set it equal to 0 and solve for x. So we have x squared plus 6x plus 5 is equal to 0. We can factor the left-hand side by looking for two numbers that multiply to positive 5 and add to 6. The two numbers are positive 1 and positive 5, meaning this can be factored into x plus 1 times x plus 5 is equal to 0. Now, by the zero product property, the only way that the product of two numbers can be 0 is if at least one of the two numbers is equal to 0. So we set each factor equal to 0. We have x plus 1 is equal to 0 and x plus 5 is equal to 0. Solving for x, we have x is equal to negative 1 and x is equal to negative 5. The zeros of this polynomial are negative 1 and negative 5, meaning this polynomial intersects the x-axis at x equals negative 1 and x equals negative 5. If you were curious, here is the graph of this polynomial. We can see that the graph intersects the x-axis at negative 1 and negative 5, as those are the two zeros. Now, what if we wanted to go backwards? Say that we are asked to find a polynomial of degree 5 with the following zeros. This problem is essentially telling us the x values for which the polynomial crosses the x-axis. So x equals 5, x equals negative 9, x equals 3, x equals 8, and x equals 0 are all values for which the graph crosses the x-axis. If we move the constants to the other side of the equation, we have the factors of the polynomial: x minus 5, x plus 9, x minus 3, x minus 8, and x. We can write these all together as the function f of x is equal to x minus 5 times x plus 9 times x minus 3 times x minus 8 times x. More typically, if there is a term with x to the first power by itself, it will be written out front like this. Thankfully, the problem allows us to leave our final answer in factored form, Otherwise, you would need to do quite a bit of foiling and distributing to get this into polynomial standard form. Notice that this is a fifth degree polynomial, as we have 5 terms, each with an x value. If you distributed everything out, you would get an x to the 5th power term guaranteed, which makes this a polynomial of degree 5. Also note that the maximum number of zeros a polynomial of degree 5 can have is 5, and this polynomial indeed does have the maximum number of zeros, 5. Now, sometimes a polynomial of some degree will not have the maximum number of zeros, due to what are called irreducible quadratics, which are quadratic factors that never equal 0 in the real number system. For example, say the factored form of a polynomial contained x squared plus 4 as one of its factors. This cannot be solved for 0 over the real number system. There is no number that can be squared and added to 4 that will result in 0. When factors like this show up in your problem, that indicates the number of zeros will be less than the degree of the polynomial. Now, you can actually solve an irreducible quadratic for 0 using imaginary numbers. For example, if we set x squared plus 4 equal to 0, we can then subtract 4 to get x squared is equal to negative 4. Taking the square root, we get x is equal to plus or minus the square root of negative 4. This is the same thing as plus or minus the square root of negative 1 times 4. We know that the square root of negative 1 is the imaginary number I, and the square root of 4 is 2, so that we have plus or minus 2i as our imaginary number solutions. Note that as the imaginary solutions come from quadratics, factors raised to the 2nd power, the imaginary solutions, often called the complex solutions if they include both a real and imaginary component, come in pairs, 2 at a time. This is the basis for what is called the conjugate pairs theorem, which states that if a plus bi is a 0 of a polynomial, then so is its conjugate of a minus bi. For example, it might be the case that 3 plus 2i is a complex 0 of a polynomial. That would also mean that the complex 0 of 3 minus 2i would be a solution. Or if you don't have the a term, like in the problem I showed you, you simply have plus or minus the imaginary part. The a plus and a minus bi come from the quadratic formula, which is your last resort for factoring quadratics. You will end up with a real component, negative b, plus or minus, and then you will end up having a term that includes the square root of a negative number, which is where the I comes from. But we have to add and subtract this value, which is why we get 2 solutions. Let's look at an example building a polynomial with complex solutions. Say we want to find a polynomial of degree 3 with the following zeros, negative 4 and 3 minus I. Now, they have only given us 2 zeros, but by the conjugate pairs theorem, we also know that the conjugate of 3 minus I must also be a 0, which is 3 plus I. So we can set x equal to each of our zeros, so that we have x is equal to negative 4, x is equal to 3 minus I, and x is equal to 3 plus I. Moving everything to the left-hand side, we have the factors x plus 4, x minus 3 plus I, and x minus 3 minus I. We can put these all together into the function so that we have f of x is equal to x plus 4 times x minus 3 plus I times x minus 3 minus I. Now, this is not good enough for our final answer, as we don't want to leave imaginary numbers in there if we don't have to. You'll notice that I've grouped the terms in such a way that we can view the last 2 factors as binomials that can be FOILed together, which makes them much easier to distribute. We have x plus 4, and then multiplying the first terms, we have x minus 3 squared, and hopefully you can see, since we are multiplying conjugates, the inner and outer terms of the FOIL will cancel each other out. You are going to have x minus 3 times negative I, and I times x minus 3, which will cancel each other out when you add them together, which always happens when you FOIL conjugates. So we just need the last terms multiplied, which is I times negative I, which is negative I squared. Recall that I is just the square root of negative 1, so I squared is equal to negative 1. We have negative 1, which is just equal to positive 1. This is all in parentheses and needs to be multiplied by x plus 4. If we needed to leave our answer in factored form, This would be our answer. But sometimes you might be asked to distribute to get a polynomial in standard form, which I will go ahead and do. First, I'll FOIL out x minus 3 squared, which is x squared minus 3x twice, which is negative 6x, and then plus 9. Adding the 9 and positive 1, we get x plus 4 times x squared minus 6x plus 10. Now we need to distribute. We have x times x squared, which is x to the third power, then x times negative 6x, which is negative 6x squared, then x times 10, which is 10x. Then we have 4 times x squared, which is 4x squared, then 4 times negative 6x, which is negative 24x, then 4 times 10, which is 40. Combining terms, we have x to the third power as our only power 3 term, then we have negative 6x squared and positive 4x squared, which together make negative 2x squared, and we have 10x and negative 24x, which make negative 14x, and finally, plus 40. This is our final degree 3 polynomial. Since this is a degree 3 polynomial, it has at most 3 zeros. But we know 2 of those zeros are complex, so there really is only one real zero. Here is the graph of this function. As you can see, the only zero is at x is equal to negative 4. You can see that this polynomial had the possibility of intersecting the x-axis 2 more times in this loop, but it didn't quite make it down to the x-axis due to the complex zeros. Alright my friends, that completes our video on building polynomials.